It's impossible to establish the one-to-one correspondence between the subset and the universal set. Set that A, B, C, D and E are infinite sets. A equals B plus C plus D and C equals E. In this way, E is a proper subset of A. As another proper subset of A, C can have the one-to-one correspondence with E, which is guaranteed by the axiom. Thus E has no redundant elements, which can correspond to elements in B or D. This simple proof is applicable to both infinite sets and finite sets. How could it be different if the elements in A and E are infinite? Let's see how modern mainstream mathematicians argue. They assume that E can have such correspondence with B plus C plus D, in that both E and B plus C plus D are infinite, and neglect the difference in the increasing speed of n. This is not a proper practice, and it is very puerile that C and E are synchronously infinite, and once the one-to-one correspondence is established between these two sets, which can correspond to elements in B or D, anyone who gives the one-to-one correspondence between E and B plus C plus D has to demonstrate why this correspondence can exist. Someone may say, this correspondence can be demonstrated by enumeration. However, this enumeration can't end because these two sets are infinite ones. Some others may say, it's enough to complete the demonstration by giving a certain method of the enumeration. Unfortunately, this argument is untenable because any method of enumeration that neglects the difference in the increasing speed of two infinite sets, which is reflected in the relation of these two sets, is pure nonsense. When we say that E is the proper subset of A, the relation of E and A is obvious. This relation shouldn't be neglected. For instance, we will analyze the statement that the set of natural numbers can have the one-to-one correspondence with the set of odd integers, which is the proper subset of the former one. The former set is 1, 2, 3, etc., and the latter set is 1, 3, 5, etc. Even when n equals infinite, the n in these two sets are synchronous. Thus the former set is twice as large as the latter one. Certainly, someone may say, this logic is only applicable to finite sets. However, have the mathematicians who claim that the infinite sets have different properties given any convincing demonstration? These mathematicians acknowledge that the one-to-one correspondence can't be established between the set of all natural numbers and the set of all the real numbers. But these two sets are just infinite sets. Admittedly, one-to-one correspondence can be established between any bounded interval of real numbers and a certain set of natural numbers, and this correspondence is the usual count, which is opposite to Cantor's demonstration for his theorem in 1890. 06. Because these two infinite sets has no relations. Someone may say, no. The set of natural numbers is the proper subset of the set of real numbers. For this refutation, we want to say that the set of all the natural numbers is the proper subset of the set of all the real numbers, but not subset of the bounded subinterval of the set of real numbers.